Hello, my name is Zachary Hedges, and this is my lab report for Physics 2, Lab 3 on circuits. The purpose of this lab was to apply principles of energy and current conservation to predict currents, measure current and voltage using multimeters, and examine resistors and capacitors. In this lab, we used Kirchhoff's node and loop rules, as well as Ohm's law. We gathered various observations based on different setups in part 1 of the lab, and we found charge and discharge rates based on resistance in part 2. Kirchhoff's loop rule states that potential difference across a loop in a circuit is zero. The node rule says that the sum of the currents entering a junction is equal to the sum of the currents leaving the junction. Ohm's law states that voltage is calculated by multiplying current by resistance. For part 1 of this lab, we examined a circuit with resistors in series. We had two 1.5 volt batteries, two resistors, one of 47 ohms and the other of 100 ohms, and two ammeters in our circuit. The circuit was the system and the surroundings were everything else. Since the resistors were in series, we could find the total resistance for the circuit by adding each resistor's individual resistance. Using Ohm's law, we know that current is equal to voltage over resistance. Dividing the 3 volts from our two batteries by 147 ohms gave us a current of 0.02 amps. Reversing the connection of one of the ammeters results in a negative reading of 0.02 amps on the reversed one. If you change one ammeter to a voltmeter, the remaining ammeter reads 0 amps due to the high resistance in the voltmeter, allowing for no current to flow through. The voltmeter reads 3 volts as there is no voltage drop in the circuit. Measuring potential difference across the circuit from the diagram gave us a +3 voltage across the battery, no voltage change over the wires, a potential difference of negative 0.96 volts across the 47 ohm resistor, and a difference of negative 2.04 volts across the 100 ohm resistor. Using these values, we can calculate the resistance of different parts of the circuit. Findings supported that the 47 ohm resistor had a resistance of 47 ohms, but the 100 ohm resistor had a resistance of 101 ohms. Across the wire and ammeter, resistance was 0. These values gave us an actual potential difference across the circuit of 0.01 volts rather than the expected 0. We can graph the change of potential across the circuit. When you attach a voltmeter to the circuit changes, but the ammeter reading does not, as the high resistance of the voltmeter results in little to no charge flowing through it. If you were to replace the voltmeter with an ammeter in parallel with the 100 ohm resistor, charge would flow through the ammeter instead of the resistor as its resistance is 0. The total resistance for the circuit would instead be 47 ohms, and the current would be 0.06 amps. The second part of this experiment had us observing an RC circuit which contains a resistor and capacitor. The circuit was the system and the surroundings were everything else again. We had two 1.5 volt batteries, a 1 farad capacitor, and two light bulbs, one of 10 ohms and the other of 20 ohms. We connected each bulb to the battery circuit to time how long it took to go dim without charging during the charging phase, and then again without the batteries to measure how long the discharge of the capacitor was. We found the charging time for the 10 ohm bulb to be 20 seconds and the discharge time to be 15 seconds. And for the 20 ohm bulb, it had a charge time of 25 seconds and a discharge time of 31 seconds. Potential sources of error in our experiment involve timing errors for the RC circuit, rounding errors in calculations, and an inaccurate multimeter reading. If you charge the capacitor in a circuit with no resistance, you would expect the capacitor to charge instantly. This cannot actually happen as all circuits have resistance in the wires and battery, even if minimal.